Hello, everyone. Hello. I'm going to check and make certain I'm live everywhere because you never know. Sometimes things are just freaking weird. And I'm starting on time. I'm on time this time. Isn't that great? That's super freaking fantastic. I'm on time. Everything's awesome. I should sing the Lego song, right? Everything is awesome. I'm going to make certain I'm going to post this everywhere that I'm live and stuff. So people can learn about atomic theory. You know? How are you guys doing? You guys doing all right? Woohoo! So today, hello. So today we are going to talk about atomic theory. Early bird gets the worm, but the second mouse gets the cheese. Isn't that funny? Isn't that funny? Morning. Good morning. How are you guys doing? You guys having a good morning? I've been up for a while. Hi. I think I'm up everywhere. I'm just double checking, you know. My audio is a bit low. Okay. Let me fix that. All right, let's see. Let me see. Let me see. What about now? Is that better? Is that better? Hopefully it's better. I can increase the properties. Let me see. Properties. Cancel that. Yay for wrenching you. That's right. Yay for wrenching. Still not as loud as usual. All right. Let me see if I can fix that. Properties. No. Let me go under mixer. This is always a big pain in the butt. All right. I can probably move it closer to me. I need to... What about now? Is that better? I hope that's better. Let me set my advanced options. Hold on. Which one is this? This is device 1. So we're going to go here and rank it up a bit. Hold on. 50. It won't. Why won't it let me do 100? It won't let me rank it up past 100%. What is going on? Anyway. All right. Okay. I don't know. I don't know what's going on. I don't know why it won't let me increase it. Wrong button. I'm trying to turn it up and it's like, let me go to, can I go to settings? Let's see, audio. Yeah, there's that one. Yeah, that's all right. That is correct. I don't know what's going on. I'm good. Okay, I'm good. Before I start touching stuff again. Oh my gosh. This is funny. It's just always funny. So, whatever. I'm trying earbuds now. Where and what is this video titled? This is called The Science of Atomic Theory. I've tried cranking it up. I'm just like, louder, louder. And it's just like, not today, Satan. Okay, now sound is fine. Fantastic. So today, what won was atomic theory. So atomic theory won out on all the others. And so today we're going to talk about the history of the atomic model. I'm not going to get heavy into quantum numbers. I'm going to save that for another episode because we could talk for hours about electrons. And so let's go ahead and get started. Whee! Oh my goodness. All right. So, atomic theory. We're going to talk about the Bohr model. We're going to talk about Rutherford. We're going to talk about Democritus. We're also going to talk about Dalton and the quantum model. Woohoo, quantum. If you think you understand it, you don't know it well enough. So, here we go. So, yes, we're going to talk about the atomic model, subatomic particles, atomic structure, essentially the history of the atomic model and how it's changed over the years. So this is all pretty cool and pretty interesting stuff. And I've already given like several talks about this over the past like few weeks, talking about atomic theory. Woohoo! The Bohr model is incredibly boring. I use that joke later, so pay attention. And you might learn something. And you might already know this too. Or this might be a refresher for you. So atomic models have changed over time. The model will likely continue to change when we get new information. In order to understand how the model has changed over all this period of time, we must go back to Democritus and early Greek philosophers. Ooh. Hey, Dragnot. How y'all doing today? So let's get with Democritus. Democritus essentially said, nothing exists except atoms and empty space. Everything else is opinion, which is true. So it's kind of like, it's interesting that we go back to, I believe this was 400 BC, where we talk about Democritus and how he was essentially going through and going, hey, we're just made up of atoms, atomos, or atmos. I think atomos, I think that was what there's atmos, the Greek word. I did not study Greek, so, that might be a problem there. I don't say words correctly sometimes. But, that's par for the course for me. So what did Democritus believe? He believed that atoms made up everything, but were mostly empty space. He believed atoms held essentially the same characteristics as what they made up. So, if we're looking at Nether 6 or Dragnot Silvis, or we're looking at rocks, or we're looking at cheese, he essentially thought that Dragnot atoms were Dragnot would be made of Dragnot atoms. He essentially thought oranges were made of orange atoms. And cheese was made of cheese atoms, and iron was made of iron atoms. So he thought that there were just smaller particles or smaller things that made up larger things. He wasn't entirely wrong, but at the same time, we know that that's not the case. But this is what, when you start thinking early on and you really don't have any kind of like technology to back up any kind of, like no real observations outside of let's think about this really hard. And so that's essentially what we're going with on that. Then walks in John Dalton. Hello everyone. Hello. So John Dalton has a really cool quote here. He says, I have chosen the word atom to signify these ultimate particles in preference to particle or molecule or any other diminutive term, because I conceive it is much more expressive. It includes in itself the notion of indivisible, which the other terms do not. So atoms are not made of atoms. So it's pretty interesting. John Dalton believed that atoms were indivisible. 1 out of 5. Yeah, that's not bad. Yeah. But, to Democritus's credit, he didn't have all the tech that we have right now. You know what I'm saying? You know what I mean? So he didn't know, but at least he's kind of like breaking it down. Hey, Andy, we have a few patrons here, Bo and Andy and Dragnot. How y'all doing today? Thanks for your support. So it only took us 50 years after that quote to split the first atoms. True. But also, atoms are divisible. They're made up of different particles. So essentially, when we're talking about John Dalton, and we do use the term Daltons when it comes to the weight of atoms, essentially, what's going on with John Dalton? Well, in 1803, John Dalton proposed the term atom as he proposed that atoms were indivisible. He drew from Democritus in the idea of the atom being like a billiard ball. So his idea was like the atom is a billiard ball. It's like a big, like a nice round ball, almost like a D20 kind of, except without the points and without the numbers, So early atom is just a big old ball. That's all it is. Where he differed with Democritus was that different elements differ from other elements. So he knew and understood the concept of different elements. You have iron, you have hydrogen, you have carbon, you have metals and non-metals and alkaline earth metals. So he understood that there were different elements. Dalton, however, was wrong about atoms not being indivisible. They are because they are made up of other particles. Hey, offensive polygon, you made it. You made it live. Woohoo. The almighty isocadron. Yes, this is a light up D20 actually. Let me see if I can get it to light up really quickly. I'm trying to drop it on the 20. It usually just does it really quickly. So this D20 actually lights up. And when it lands on what they call a nat 20, natural 20, this D20 lights up on that. I am that nerd, and sometimes I teach my public in science communicate with various things, including dice. Everything can be improved when including D&D. Oh, look, it lit up. Crap. I set it down. I set it down, and then it stopped lighting up. It's like, there it goes. Oh, crap. Light up. I know you light up. You're a Christmas present. Anyway. So, oh my goodness. So, yes. And it lights up off camera, of course. It's like that frog from the Warner Brothers cartoons. Hello, my baby. Hello, my honey. Hello, my ragtime gal. Only dances for the one person that's watching. Never for anybody else. That is my light up D20. Hello, everyone. Hello. So we're talking about atoms. Let me get back on topic. Next walks in Joseph John Thomson, and he developed what we call the plum pudding model. The plum pudding model being that an atom is a spherical cloud that has both positive and negative charges. And use it to hit the dice. I'm actually drinking some orange juice right now. I'm drinking a little bit of orange juice at the moment. I have on my Doctor Who hoodie. And I have my Doctor Who, see. It doesn't, it's a weighted thing. It has to land on the D20. It doesn't light up unless it actually lands on the 20. It's one of those things. It's a double slit experimental dice. Yes. Hello. TARDIS, yes. So Joseph John Thomson proposed this plum pudding model. And so what exactly was the work that he did associated with the atomic model and all that jazz? Because it's kind of important we understand, we also have to be able to prove things. So in 1904, Thomson used cathode rays to discover the existence of electrons. He first called them corpuscles. Now, we don't call them corpuscles now. We call them electrons because, you know what, that just sounds sexier, doesn't it? Corpuscles kind of sounds like some kind of weird disease thing. Oh, I'm sorry, my corpuscles are interacting with your corpuscles. That just sounds nasty to me. Electrons, though, that just sounds way better, doesn't it? Electrons. Electrons are just kind of really sexy sci-fi kind of sounding stuff. Corpuscles, nobody wants that. Anyway, he did win the Nobel Prize for his discovery. Now, his particular model shows the electrons scattered out in a cloud, which is correct, but he did not know that there's a positively charged nucleus in an atom. His model is called the plum pudding model because it resembles the dish known as plum pudding with bits of fruit spread out in it. So that's kind of important to take into consideration, and there's a little bit of difference. UK pudding is different from American pudding. So so UK pudding is like, oh gosh, I have to wrench you. You're going to have to, I guess I need to wrench you in, let me see, how do I do that? I have to go to your channel. I don't know how to wrench you while I'm doing stream right now. Gosh, I'll wrench you later. Look at pig. Oh my goodness. I guess I could. Let me try to go to your channel, I guess. Let me go to your channel here. There we go. Now, okay, thank goodness I don't have, okay, I'm sorting it out. So let's talk a bit about the difference in language between like the UK and the US version of pudding. Our pudding is kind of like a little bit like, it's, oh gosh, it's the gooey pudding and it's got vanilla or chocolate. But the plum pudding there is more like a muffin, kind of. That's what they consider a pudding. So the plum pudding model is a bit like fruit cake. For those of you who are American and they're like, what is this plum pudding that you're talking about? Who is that Bob the dog? Where he from? English pudding is the only pudding. You know what would be cool? I need to do this next time I'm in the UK. Make a pudding. Make an Atlantic pudding. Take one of their puddings and fill it with American pudding. But then you guys call that pudding custard. You guys call that pudding custard, which is weird to me. I'm like, I want to give you a wrench here. Look at pig. Hang on. I've got to go. There's so much clicking involved. And then YouTube is just like, what's up? I'm like, gosh, man, you guys are a pain. YouTube is a pain sometimes. And I say this not because I hate YouTube or anything, but sometimes they're just really, they just kind of get on my nerves. It's all in the pudding. It is all in the pudding. Steak and kidney pudding. That just sounds gross to me. Pudding from England is the only pudding. Pudding from England is the only pudding? Are you sure about that? Oh my goodness. Your pudding may not be my pudding, and that's okay. I do like different kinds. We have custard on the pudding. No, but custard is like more runnier than pudding. It's not the same. I don't think it's not the same. I've made banana pudding. I thought I copied and pasted this. Let me copy and paste again. Paste. Yes. I have wrenched you, look a pig. Changes have saved. All right, I'm going to downsize that. Yay. I have a separate live chat through Streamlab. And then I'm also looking at Restream. So it's kind of different because I have like several different chats going on. All right, you like bread pudding, Bob the dog. I like bread pudding too. Have you made bread pudding from donuts? For real. If you've not made bread pudding from donuts, you should give that a go. Hello from Glasgow. Hello. All right. So now we're going to get to Rutherford. Ernest Rutherford. What a smart guy. Banana and custard is a great combo. Yummy. So Ernest Rutherford. Now I know what the atom looks like. Ernest Rutherford is a pretty smart dude. Bread pudding is like a saucy muffin. So let's talk a little bit about what he did. He did something called a gold foil experiment. And so essentially he took a radioactive sample that emits what we call alpha particles. Alpha particles are positively charged. And so what he did is he blasted it through the gold foil. And he found that a lot of the particles passed right through it and they hit the zinc sulfide screen. The zinc sulfide screen then reacted to those particular alpha particles and you could detect it that way. And so the thing is as it was going through, some of these particles were deflected in all kinds of different directions. Now, since alpha particles are positively charged, they should have either been like more drawn to the electrons, and they weren't necessarily completely drawn to the electrons all the time, which means they passed right through, passing right by those electrons, signifying that there's mostly empty space. And also, since there were some that were deflected, it showed that there's also a repulsion. And since there's a repulsion, that means that those positively charged particles were repulsed by something. Well, what repulses positive charged things? Other positive charges, which shows that there had to have been a nucleus. So the Rutherford model looks like this. If I can click. I know you guys hear my click. There we go. Rutherford model of the atom. How quaint. Isn't it lovely? It's got our little orbits that go around our positively centralized nucleus, and we've got our electrons that go around there. So that's essentially kind of what the Rutherford model is. Hello everyone. Hello. So when we're looking at this, yay. So when we're looking at this, essentially what we're talking about is kind of like the Rutherford model, and it's a difference from the Dalton model, and that the Dalton model was this billiard ball, and then we get the plum pudding model where everything's just scattered about like, you know, fruitcake, plum pudding. And then we get to the Rutherford model where we have a centralized positive charge and electrons that kind of go around it in these little looking like Jetson type of atom, you know, so that's cool. Stop stray electrons around the aperture in the gold foil. Yeah, true. Yes, gold is chemically inert. And yeah, so that's why when you have, if you were to partake in Goldschlager, you could drink that and you can have gold particles and it doesn't do anything to you. Now there is, as an aside, having worked with gold nanoparticles in research, there is some concern as to what actually happens with gold nanoparticles if we were to use that in the body. So if we were to go through and use that as a drug delivery system, they don't know what the collection of the gold does over time, especially if it happens to collect in various organs. Even though it's chemically inert, are there any other types of things or problems that can arise from gold collecting in the body? So that is a particular thing associated with gold that we don't quite know. So, excuse me. So far we've talked about the Dalton model. We've talked about the Thomson model. We've talked about the Rutherford model. What other models could there be? You thinking? Who comes next? So let's talk about what Rutherford got right, and let's talk about what he got wrong. Hello. Rutherford got a few things right, and he got a few things wrong. He got it right about the nucleus. There are protons and neutrons. He also got it right about electrons orbiting the nucleus. But what he didn't explain is how is it that electrons remain in those orbits around the nucleus. So enter the epic, exciting, and boring Niels Bohr and his planetary model. You see what I did there? You see what I did there? It's an incredibly boring model. It's boring. I have lots of dad jokes, and I know you guys love my dad jokes. Niels Bohr is correct. Yes, I believe Nether and Bo. You guys got it. Niels Bohr. String theory of the universe as compared to atomic theory. String theory is something different, entirely different. That's like saying, let's compare cows to oranges, in my opinion. So it's like cow theory versus orange theory. You're like, string theory is completely different. It's something else. It has to do with multiple realities. And the reason why they kind of think about string theory a bit is because we do have different particles that kind of phase in and out of existence. We're like, what the heck is going on? Can't always trace them. Neutrinos being one of those. We know neutrinos exist, but it's kind of like, there's that neutrino detector in Japan where every time neutrinos flash, there's like bright lights and stuff like that, which is pretty cool. So now we've talked about Democritus. We've talked about John Dalton and his billiard ball model. We've talked about Thomson pudding model. Now, then we moved on to Rutherford with a little, the iconic spacey looking type of atom, C.S. Lewis type of thing. And then we get on to Bohr. Yes, Bohr was super. That's the thing. I think it was Newton's like you're standing on the shoulders of giants. To be quite fair, Democritus was pretty profound, sitting there saying we're made up of smaller parts. It's like we're smaller things that put us together to make us who we are. Even though he got everything else wrong and we're like, oh, well, that was so wrong. But to not have that previous knowledge, you have to have a starting point for thought. And so that's a lot what you're talking about. Yeah, and Bohr's electron shell model was pre-quantum theory. That's true. But you just kind of add on to that. It's the subatomic of subatomics. It is, if we're going to get into string theory and the shifting of particles in and out of existence, where do they go? We don't know. That's kind of weird and cool too. So there's a lot of different stuff. So I am U.S. I'm in the southern U.S. if you're curious. So, and I do have a Discord, and Look a Pig has been working on that, of combining several different science communicators and different types of skeptic communities to kind of bring us all together to where we have one spot to where we can all kind of contribute and be a part of, which is awesome. So, yes, applications of the isotopes of gold in medicine and industry, very true. My hair is cool. Thank you. Thank you so much. I appreciate that comment. I like my hair. So now let's talk about the boring Niels Bohr. What you got there, man? And I think I'm overlapping on his quote, so I'm sorry about that. Essentially, it says, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Which is true. If you are not utterly and completely surprised, hello Shane, if you're not utterly and completely surprised by quantum mechanics on any given day, it's like you haven't understood. You're just like, why is it doing this thing? This does not make any kind of sense. This is so strange and completely opposite to what we see in the world. Quantum level stuff behaves very strangely. All right, so essentially, Niels Bohr, he put electrons in orbit, and he also helped explain something incredibly important known as spectral lines. Spectral lines are pretty cool, and it's what we use to determine the compositions of different things, because elements, compounds, giant freaking molecules have very specific types of spectral signatures, and they can hit at different points on the visible spectrum and different wavelengths. So if you think you understand quantum, you don't understand quantum. I think that's pretty much. I can't remember the scientist who said that. Goodness, it's like if you think you understand quantum, you don't understand quantum. I got quantum tunnels in my phone. Quantum tunnels, that almost sounds like, I'm sorry, I got quantum carpal tunnel syndrome. You know, it's like, can you have carpal quantum tunnel syndrome? Is that a thing? I have quantum tunnels in my hands. I can't come to work today. I wonder if I could use that as an excuse for work. I'm sorry, but my quantum tunnels are acting up in my joints today. I have to stay home. Feynman said that. Thank you. Feynman said that. If you think you understand quantum, you don't understand quantum. Coincidentally, I had to take the physical science ACS chemistry test as for when I was getting my master's. I was getting my master's in chemistry. That was our final. I'm sorry, for physical chemistry, not physical science. For physical chemistry, the physical ACS test was what they used for the exam. I scored the highest in quantum and nothing that the teacher taught in class, which was mostly thermodynamics. I love thermodynamics and I learned a lot in that class, but I was quite proud of myself that I understood quantum chemistry. And that was stuff he didn't even teach. And my physical chemistry professor looked at me and he said, "Your test just tells me you should just teach yourself." I know. If I don't understand quantum, then do I understand quantum? Probably. I think the point is you cannot understand quantum. Quantum. I have been up since 5 a.m. And if you check the tail end of Side Strike's movie night, you will find me at the very end on his movie night, which they ran for 7 hours last night. I was only on the tail end of that, which was funny. Oh my goodness. That's pretty funny. So let's talk a bit about the Bohr model, because it's boring. The Bohr model. So here it is, right here. So he gave us what we call the planetary model, because it looks like there's a sun in the middle with the planets going all around it. So essentially we got a nucleus in the center that's positively charged. And then we have these electrons orbiting it around the outside in these very well-defined orbits. Well, here's the thing. There's electrons don't behave this way. They're not in well-defined orbits. They often don't behave at all very nicely. They do all kinds of different things. So to think that they go in these particular circles like that, so nice and neat and uniform, that's not reality. So that's pretty interesting. Bohr, yay. I'm not sure about Heisenberg. He has no principles. He's uncertain about his principles. What you talking about? What you talking about? So let's, I want to talk a bit about the experiments that Bohr did. The experiments that Bohr did was pretty freaking important because he was able to definitively prove that electrons can jump from energy level to energy level. This is actually pretty important. So what he was able to do is he played around with hydrogen. And so he was looking at hydrogen, and he noticed if you blast it with light, it jumps, it like absorbs the light, and then it releases what we call spectral lines. So let's have a look at this, like a little bit of this particular animated GIF. So here we've got, and we get like our principal quantum numbers here, but essentially what that little red little squiggly line is over here. All right, we've got light coming in. Electrons get excited. They jump up to the next energy level. And when they calm down, they release that particular bit of photons that gave them that energy to jump up to the next level. And all of these different N1, 2, 3, 4, 5, those are different energy levels. And it requires a different amount of energy in order to achieve those jumps for each particular level. The higher levels, there's less energy that you need to go from like 4 to 5 as there would be from even 1 to 3 or 1 to 2. That requires a lot more energy than going from like the 4th to the 5th. So what does all that mean? So that's what we were seeing when that little electron is going up. It would get blasted with light, and then we go bing, and it would jump up, and when it releases, it releases light at a specific type of spectrum. And so when we're talking about the visible spectrum, we've got our Roy G. Biv, you know, our red, orange, yellow, green, blue, indigo, violet. Those all have different wavelengths. And that's what our eyes pick up. And so we kind of have to understand a little bit about that. So there's different wavelengths. So when that electron releases, it releases light at a very specific wavelength that is indicative to just hydrogen. It's amazing. All right, so that's what's cool about that. And my whole analytical chemistry degree was just based on detecting stuff. And so when Bohr worked with hydrogen, he showed that light causes electrons to jump to higher energy levels. Now, when they relax, they release those photons, and that gives us what we call spectral lines. So if you didn't know what spectral lines were before today, you do now. And we use that all the frickin' time. So light travels. Okay. I did a whole episode just on photons, my ass is dragging. I did. And I talked about how, all right, the broader the wavelength, the less energy the photons have. The shorter the wavelength, the more energy the photons have. So that's why we have different types of electromagnetic radiation. So when we're talking about X-rays, when we're talking about gamma radiation, when we're talking about UV radiation or visible light or infrared, that's all based on the size of the wavelengths. So the ones that are really close together, those waves that are really close together, that has a lot more energy put into it. So that's kind of where those photons are just like up and down, up and down, up and down. They move like waves. So as it's going up and down really, 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 really fast, if you hit something with that, that energy is coming from those photons moving at those particular types of wavelengths. So you're finally home from work, Andy. Yay. So the energy comes from those particular wavelengths of photons. And so this is why, for instance, gamma radiation. If we're looking at gamma radiation, we talk about the Hulk. He took all this gamma radiation. Gamma radiation is so strong. There's so much energy there. Those photons are so close together on those wavelengths and moving at such a high speed that it breaks apart chemical bonds. It actually breaks apart molecules. This is why you have radiation poisoning. And so for like radio waves or microwaves, those are really far apart. So it would be like somebody punching you like this. Or if we're talking gamma radiation, like really hard over and over and over and over and over again. So that's essentially what we're looking at. EM drive technology, electromagnetic drive technology. Is that what you mean? I'm not certain about that technology. I will have to look that up now. Maybe do a show on it. Just say EM. It's way easier. EM radiation. Spectroscopy. Yes, Anthony. This is where spectroscopy comes into play. For instance, proteins. Proteins absorb light at 280 nanometers. I know this because I worked in protein recombination, and if we wanted to be able to determine how much protein was in a sample, we blast it with light at 280 nanometers, and then that absorbance can be translated to a concentration. And depending on the protein, you can have an extinction coefficient for that. You can back calculate and determine how much protein is in a sample. DNA hits usually around 260 nanometers. So if you blast a sample at 260, you can kind of determine how much DNA is in a particular solution. So that's kind of what we do with that. All right. So for this, Bohr's discovery was extremely important, and his work was important because it gave a better understanding as to how light affects atoms. Electrons get excited when hit with certain wavelengths of light. This led to research into how the different elements have their own fingerprint signatures and what wavelengths of light they release when their electrons relax. What Bohr got right were the electrons and energy levels, but it doesn't really explain how heavier atoms don't have their electrons completely collapse into the massive nuclei full of protons and neutrons. Now we see Schrödinger and Heisenberg jumping into the equation. Or didn't they? Did they? Or didn't they? Oh, goodness. So, oh, Ian Drive in that show. Oh, are we talking about Star Trek? Okay. We are all excited. So now we're going to talk about, gamma radiation isn't cool. That sounded hot. Well, infrared wavelength, that is pretty hot. It's heat. It is heat. I'm catching up on all the comments. Doh. Oh, goodness. Morning. Good morning, everyone. We are on Saturday Science. Oh, goodness. You'd get more thrust with a high-powered flashlight. Probably. This is the truth. Now we're going to get to Schrödinger. Who's Dinger Schrödinger? I don't know what that means. It's like a buzzer. Zzz, zzz. Is that it? Is that a Schrödinger? What would a Schrödinger sound like? If he had his own buzzer, what would it sound? It would have to be at least 2 different sounds. Wouldn't that be it? A Schrödinger would have to be at least 2 different sounds. I've got Science Saturday, and they've got Sunday Science. Andy has Sunday Science on Sci Strikes channel on Tuesdays, usually. So that's a little shout out for that. So here is a quote from Schrödinger. A careful analysis of the process of observation in atomic physics. So we're going to say a lot of sciencey words. A careful analysis of the process of observation in atomic physics has shown that the subatomic particles have no meaning as isolated entities. By themselves, they're worthless to him, but can only be understood as interconnections between the preparation of an experiment and the subsequent measurement. What does it all mean? What does it all mean, guys? Or Wednesdays. True. Oh, goodness. The slapping sound you made with your fist. Oh, goodness. I was trying to prove a point, guys, about, either have like the really slow microwave. It's like, like, it's going to get me. This is going to get me. Or you're going to have like the gamma radiation where it's just over and over again punching you in the face really hard. That's the best analogy I think I can have for that. And this requires a lot of energy to do that. So, it's just like... But yes, so what does that mean? So even when Schrödinger's going through with that quote alone, man, that's a pretty powerful quote. So when you're looking at atomic physics and quantum, it shows that the subatomic particles have no meaning by themselves. Essentially, they're kind of useless when you just look at them by themselves. It's not what they are by themselves, but how they interact with each other. And they can only be understood on how they interact with each other. So when you're preparing the experiment, trying to study how they interact with each other, the measurement of that is exceedingly important. So that's kind of what he's breaking down there. He took all these really fancy words that sound terribly important, but what he means is like, the little bitty parts are not really as important as the sum of them all together, interconnected and working with one another. That's kind of what we're looking at when we're dealing with quantum. Quantum, the particles by themselves, you're like, well, they kind of do this stuff over here, and then they do these things over here, and then when they get together, they do this thing entirely differently that you wouldn't totally expect all the time, but this is what happens. So, just because science, right? We coined that when I was at NASA, because science, That was so much fun. I really should go to another NASA social. And cross your fingers. I did apply for their science solar ambassador position. So hopefully I'll be able to get and be one of their professional science communicators to do different outreach stuff for NASA. That would be really cool. It is a voluntary position, but cross your fingers. I do have a shiny new Discord that Look a Pig worked very hard on, and I will be talking to you after the stream like I promised. So we'll get it fixed. And as an aside, I'm working with Katie Paulson from Pathos. I've got a really cool new show coming up called BS, This Week in BS, where she and I will break down the latest and greatest in bad science. And we'll even talk about stupid things celebrities do. So that's a little nudge for Katie's in my show coming up soon. So back to atomic theory because it's incredibly exciting. So what happened? Well, in 1926, Schrödinger, along with Werner Heisenberg, proposed that electrons, like light, move in waves. Cool, dude. Point break, right? Heisenberg and his uncertainty principle discusses that the more you know about the location of a particle, the less you know about the momentum, and vice versa. If you know its momentum, then you know less about the location. If you know about the location, then you know less about the momentum, about its movement. You know less about its movement, the more you understand where it is. So this is a problematic. Now, Schrödinger used thought experiments to also discuss that just by observing the universe, you change its behavior. We know that light affects electrons, so we cannot possibly know everything associated with atoms, because when you look at an atom, you need light involved there. What happens if light's not around? Who freaking knows? So we cannot possibly know everything. So how do we solve this atomic model conundrum? They used math or maths. Depends on our mathematics. We could say mathematics. In order to determine the probability that an electron is in a particular area. This gave a three-dimensional structure to the different orbitals of an atom. His equations take into account these three types of coordinates: the principal numbers, the angular numbers, and the magnetic quantum numbers. These numbers describe the shape, size, and orientation of these orbitals of an atom within space. Now, it is our best model to date for describing what we know about atoms. So, uncertainty principle. The blue math guy. To be fair, Breaking Bad, the teacher there just took Heisenberg's name and he called himself that, that's like a really, really, that's a really bad thing. You're turning Mel into a shill. Call me there after you joined. But does that mean everything is made of nothing on a subatomic level? That's weird. So Marty, you got to think everything is made of atoms. Atoms are made up of subatomic particles. But when you get down to the subatomic particle level, you're dealing with particles. You're not dealing with people anymore. You're not dealing with animals. You're not dealing with rocks. You're just dealing with the particles by themselves. So we're all made up of subatomic particles, but it's those interconnections between those particles. And then once you make the atoms, then the interconnections between the atoms. It's absolutely fascinating and amazing. We are but atoms studying atoms. So insert your existential crisis of the day. I have at least one every day. I haven't had one actually in a few days. So right now I'm having one. We are but atoms, studying atoms in a vast, ever-expanding universe that's falling to bits due to dark matter. And we don't know what makes that either. I am but a hairless ape on a spinning planet in an ever-expanding universe that's going to bits. Oh my goodness. It's all just crazy, isn't it? Microwaves are like a pea shooter. Gamma is like a machine gun. That's right, Dragon. You got that. That's got it. It means something. It means something is nothing. It kind of puts everything in perspective. Why am I paying bills every day? Why am I doing this? Why am I talking about science? Why is it that we are doing these things when we're just really made up of subatomic particles that are utterly useless by themselves unless they were interacting with other things? Oh my goodness. Ah, this just, man, I'm catching up. I'm catching up on everything. I feel it's unlucky to be superstitious. Oh, okay. 3 Blue 1 Brown made a great video about uncertainty principle. That's awesome. I'm uncertain about that. Somewhat simple terms. How is neutrinos involved in our daily lives? Does a neutrino mingle with the atoms? How does the neutrino form? Oh, goodness. Okay. So neutrinos are subatomic particles or teeny tiny things. They just phase in and out of existence and they pass through us. I don't know that much about it. I did talk about the various subatomic particles in another episode, but I talked more about what they individually were. I didn't talk about their origin, and I didn't talk about, they don't really do anything to people. They just pass through us. It's like the force that passes through us. It binds the universe together. That's neutrinos, I guess. That's pretty much what we're going. They don't really mingle with atoms. They just kind of pass right through us. I really kind of need to look up more on neutrinos at this point. I feel like I would do that. Quarks. Yay, quarks. Fantastic. What caused this great stuff? Does there have to be a cause for the great stuff? I keep getting anxiety attacks. I get those sometimes too. That's really, really weird. We are as old as our atoms. This is true. And we are made of star stuff. Let's see. Carbon, hydrogen, oxygen, nitrogen. Everything that's found in stars is found in people, except for helium. Helium is the only element. As far as like the majority of the elements in the universe, carbon, hydrogen, oxygen, nitrogen, and helium. That is the majority of elements in the universe. We are made of the majority of elements of stars, except for helium. That's it. Yeah, the universe doesn't care. Us hairless apes have just as many hair follicles as any other ape. True, we do. Niels Bohr and Ernest Rutherford. There you go. Oh, goodness. Our neutrinos are fermions, and only the low energy ones sometimes interact with atoms. 99% of them just pass through the planet. True. You got attacked by a lizard. A lizard fell on you. Oh my goodness. You guys are funny. So let's take a look at the quantum model. You guys want to see that? Here we go. Check this out. You have all of the different orbitals. Look at that. You got S, P, D, and F. Man, don't get me started on F orbitals. F orbitals, I don't talk about those. F orbitals give me panic attacks, man. I go back to freaking inorganic chemistry. I want to cry thinking about F orbitals. It was just awful. I'm like, I don't talk about F orbitals. D orbitals, barely. I'm a biochemist. I have a biochemistry background. So we can talk about S and P. I'm cool. Do not get me started on D and F orbitals. Not my jam. I don't like those. D orbitals you find mostly in the transition metals. F orbitals you get into the lanthanide and actinide series, and you're just like, let me just rip out my hair to keep, I shave my head to keep from ripping out my hair. So it's just like, man. But that's the quantum model. We know that within those particular cloudy areas, we can find an electron. So quantum model right there, guys. That's the best thing we got right now. How cool is that? And we can kind of see the spectral, the emissions that way. So it's kind of neat. That's our best option at the present. It's a quantum model. So let me show you like a little cartoon. I'm going to show you a little cartoon here of the different orbitals, in case you're wondering. So yes, so we have the S orbital here. Here's the S orbital right here. That's like when you're talking about hydrogen, its orbital looks like this. So there'll be an electron somewhere in this particular cloud. Then we get the p orbitals. This is what carbon does. Carbon bonds here and carbon bonds here. All right. And so we got our XY plane. All right. Now we have our d orbitals. So we know within these clouds, electrons will be in the clouds, not in the nodes. You're not going to find an electron here. You're not going to find an electron here or here. You're going to find them somewhere within this cloud, in this three-dimensional cloud. And then we get f orbitals. Not only do we have, flat, we have x and y planes. We also have a z plane here. F orbitals make me want to scream. Hello, Cliff Jumper. Hello, everyone. So we're like, gosh. So we got this z plane here, x and y. So the f orbitals, I don't play with. But you would see, essentially, within these little particular nodules in these clouds, the nodes are where they meet. You were not likely to find an electron here. You're likely to find an electron out here. So I will discuss quantum numbers, but in another show, not this particular show. So let's chat a little bit before I kind of sum up everything. Why do we waste helium on balloons? That's a good question. And the thing is there was like a real problem with the environmental issues with people releasing helium balloons into the atmosphere. They do eventually pop and sink back to the earth. So, it's a form of pollution. So, you got to be careful with that. Goodness. Why do F orbitals make you scream? There's so many orbitals. That's why they make me scream. Just trying to get through organic chemistry with the p orbitals and all of the different energy levels associated with each one of those, and drawing like your bonding patterns. And if Dragnot was around, he'd be sitting there going, p orbitals, man, don't get me started on F. Dragnot would actually, because I know he's taking organic right now. The p orbitals, once you get into all the different ways that carbon can bond within p orbitals, and then you go to d orbitals and inorganic and start worrying about that and the transition metals, and then you hop into f orbitals with lanthanide and actinide, you're just like, God! Hello, star hearts. You're just sitting there and you're just like, oh my God, gosh, all of the different ways that carbon can bond with p orbitals alone. And then you get into transition metals and the d orbitals and all of the different crystal structures associated with those. Then you get into f orbitals. You're like, I'm done. I'm done. I'm done. So that's just how I am with orbitals. And it's just, after a while, you're just, ooh. Pi and sigma bonds and hydrocarbons. You remember that well. Sometimes you wake up screaming. Then, yes, exactly right. Is it a pi bond? Is it a sigma bond? Is it 2p, 3p? Which p is it? And you just go through all that. And then you get to the d orbitals. You're like, I already went through organic. I was required to take inorganic for my undergrad in biochem. I didn't take it for my master's. I completely circumvented that. It's just like, that's over there. Oh my goodness. Bye, Slim. Have a good weekend. So that was all that. Makes more money. Oh, yeah, entertainment does make more money than science now. See, you're right. So orbitals are not my favorite thing to talk about. Well, like the F and D orbitals. Not today, Satan. Not today. So I have a pretty cool breakdown graphic of stuff I'm going to show you on a big monitor. There we go. So we have Democritus first proposed his atomic model. It's a round sphere, all right? And then, you got like no electrons, no protons, no nothing. He just essentially thought buildings were made out of building atoms. People were made out of people atoms. Cheese was made out of cheese atoms. Then we come over here to Dalton. And he thought, okay, it's got to be like a billiard ball. We got to have that going on. It's round, and I know that. You're like, okay. And then we move over here to Thompson, and he had his plum pudding model where you have like positive and negative charges all kind of spread out like bits of raisins or like in a fruit cake, you know. And then we're like, okay, not quite. And then we get Rutherford, who's like, okay, we got a nucleus, but we have electrons that kind of go around this nucleus. So they're getting closer, right? And then we got the planetary model by Niels Bohr. And then he went through. And then we got like the centralized nucleus still, but we have defined orbits. But that doesn't really explain how heavier atoms don't have like pulled electrons into itself. Excuse me. Hang on a sec. I think I stopped coughing now. Try cutting that pudding in half, right? All right, so then we've got Heisenberg and Schrodinger and their quantum model, which makes way more sense. And we've kind of gotten a lot of evidence to support that, especially through um, different types of spectroscopy and being able to kind of look at those shapes associated with that. Oh my goodness. I'm almost over whatever this is that's had me sick. What holds atoms together? Well, I think I've kind of gone through that. There's different energy levels, and then these particular, you have a certain amount of protons and neutrons in the nucleus. And once those protons and neutrons kind of interact together, they form a stable nucleus. Then you have electrons, and you have electrons that can kind of that position themselves within certain energy levels that kind of form around that particular nucleus, and they orbit within those clouds. And then the outermost shell, the outermost energy level, is where all the binding happens in between atoms, where the electrons can come and go. But certain types of atoms cannot be without a specific amount of electrons, or they become unstable. Yes, that's true, Nether. They are held together by the strong nuclear force. Yeah, and we've kind of talked about that. Oh my goodness, you guys are funny. Ah, so that's what we've been talking about. So now they're worth something. So essentially what we talk about when we talk about this atomic theory model, the model of the atom has changed throughout the years, and it can change again when we get more information, which is okay. That's all right. That's kind of how science works. So far, the current model is working well with what we know in our natural world. Now, as an aside, if you want to learn more about atomic theory, you can hit me up on Twitter in the comments here on my Facebook page. I'm not actually listing any sources for this particular episode, as there is so much information on the internet, and all of this is literally textbook material. So I don't always put sources up for standard theoretical type of knowledge that's considered general knowledge among the scientific community. It's just general consensus. So, textbook information. That's essentially kind of what this is. But there is a vast misunderstanding of atomic theory and particles and things like that. So that way, I wanted to, when this won out, I wanted to make certain I talk a bit about the history of it. Because not everybody knows everything, and that's all right. But we got to kind of like take it down there. So I will post as a topic option all the things associated with electrons, so we can talk about electron configuration, binding, and that sort of thing. For those of you who are up for that, you can vote for it on Twitter. I post all my polls on Twitter, and I'll probably post a new one today, guys, so we can go ahead and get that rolling, because I like to make little trailers for all my different shows, if you haven't noticed. So if you haven't, please subscribe to my channel, like, share. All of my stuff I offer for free. My website, ScientistMel.com. You can go there. I put my slides there. I do need to update that, so I'll be doing that tomorrow. So all of the access to all of the stuff that I've done here, you can use freely for yourself. Just give me a little nod. Hello, Mrs. Snarky. So that is what we have been talking about. The science of atomic theory. Now it's not so scary. And I give you guys A's for showing up. Good job. I'm proud of you. Sometimes this is hard stuff and not everybody knows everything, and that's okay. That's okay. So I'm going to take a moment to thank my amazing patrons. They make what I do possible. Tony, James, Lauren, Jen, Carl, Melanie, Patrick, Daniel, Stephen, Paula, Tim, Carrie, Cersei, Keith, Duke, James, Andy, Zachary, Tony, Bo, Stephen, Sarah, Chris, Graham, Dragnot, Godless Iowan, Jennifer, Corey, and Richard. And I have a new patron. I needed to add him today. Let me find him really quickly. I'm going to find him really quickly because I want to give him a shout out. I sent him a message. I haven't added him to the new slide yet, but I'm gonna. Neil. Thank you, Neil. I'm giving you a personal shout out for being my latest and greatest patron. So thank you so much, Neil, for hopping aboard and contributing to my work. I'm often in the hole every single month because I do spend my own money promoting science literacy in the form of social media ads. In addition to buying new equipment, I have a website. I also pay for apps that I use to generate content, as well as streaming to multiple platforms, trying to get the message out as much as possible. I do pay for that. All of the money that my patrons give me go towards those efforts. I don't make a dime, and I'm often in the hole. So I have to say a special thank you to my patrons. Thank you for your help. It means a lot to me, and I love doing this, and I make all of my stuff available to teachers. I have teachers contacting me now who tell me they use my stuff in their classrooms, which is absolutely amazing. And I hope to start streaming and working with different teachers who have after-school activities for their students to Skype in and do video chats with them, as well as help them develop programs for girls in STEM. So I am doing outreach work within the community, and that's very important to me. It's something that I want to do. Where can you find me, guys? Everywhere on the internet. I'm also on Twitch. I'm on ScientistMel.com, Patreon.com/ScientistMel. That's where you can find me. Periscope, YouTube, Facebook, and Twitch. All of that is there. And you can check me out there, join in, tell me the things that you want to learn about, because I'm here for you guys. I am here for you guys, and that's what it's about. Let's see. I'm catching up on messages. I don't know what a God rate is. Okay. Oh my goodness. Okay, an error occurred. I don't know what it is. Can I build a small nuclear reactor for personal use? I'm tired of paying for electricity. I would recommend solar. Solar is probably your best option, solar panels. All right, solar panels would be good. And I think out west they can rent them, kind of like a satellite TV type of thing. You can rent solar panels. Wind power is cool too. That works. Let's see. We have a few deleted messages. I don't know what that is. Somebody must be moderating. Not today. Oh my goodness. Oh boy, we got people that are trolling. That's a shame. Oh, thank you. How many atoms are in Mel's hair? It's really thick. Here's something interesting, and I used to talk about this when I taught biology. Protein. Protein takes a natural form. So my hair is essentially made of keratin, right? It's protein. And so curly hair has a slightly different protein structure than straight hair. And so the thing is a lot of proteins are based primarily on hydrogen bonding among the molecules. So you'll have hydrogen bonds that form between different particular molecules on a protein molecule. So you have a huge protein, and then it curls up like that because that's its natural configuration to interact with other portions of the molecule. So in order to straighten my hair, I have to add heat and break those hydrogen bonds that my hair naturally forms in order to make it curly. And if I go long enough without it, it actually will start to form dreadlocks and connect to itself and form those hydrogen bonds with other strands. And so in order to break those bonds, you have to add heat. And so when you add heat, you can flat out iron your hair. And it would take me 2 hours to do that. 45 minutes for 3 hairdressers to flat iron my hair in order to break all those hydrogen bonds. It's crazy. It's crazy. I don't know how many atoms are in a strand of one of my hair. We would have to sit there and look at a keratin molecule and figure out how much keratin is needed to make a hair follicle. And then go through and determine how many hairs are on my head. And then we can multiply that way. But I would have to go through, in order to conceivably do that, measure my entire head, figure out how much area is there, and then take a small little area and figure out how many hairs are in like a millimeter of my hair, and then figure that out. And then once I get that, set that number aside, then I'd have to look up keratin and see how much keratin is in the average hair strand. And then, after I figured out how much keratin is in the average hair strand, have to determine the length of that, and then consider the length of my hair when it's not curled. Then I could calculate how many atoms at that point. I don't know that I want to do that, though. But if anybody else does, let me know. Oh, my goodness, the CCP. Of course they decided to troll my chat. What's new? They'll probably make a video about me calling me a Nazi again. I don't care. I don't even watch their stuff at all, man. Make videos about me. That's great. That just sends more people to my channel. It means they get to hear actual logic and reason more often. Just buy an electron microscope. They're not expensive. No, man, that's cheap, isn't it? It's so cheap. Yes, do not spam the live chat. I have wonderful moderators. Thank you guys for looking out for me. And Bo is one of my patrons. Thank you, Bo. It wasn't the CCP. It was a random raid. Oh, okay. Thanks, Look a Pig. It's funny how that works. I guess I'm going to get me some more orange juice. I'm almost over whatever this is. This is week 2. This is week 2. NyQuil every night, guys. Every single night, NyQuil. DayQuil every day during the day. Every single night. Every single night. I'll let Look a Pig fill you in on that. My ass is dragging. Is that like molasses? Oh my goodness. So, if you have ideas for my show, let me know. Let me know. I do these shows for you guys. I want to help you, educate you, and help you guys out and give you accurate information. I am enjoying, thank you TT for being here. I'm so glad you've enjoyed my talk. Is keratin made of silicone? No, it's not, but that'd be cool if it was. That would be pretty cool, David. Your hair has molecules. Yes, it does, TT. I'm catching up on everything. Trying to. Spreading. Okay. Alrighty. Oh, let's see. I'm catching up on comments. 20 to 30,000 hairs. Wow. I would assume mine is probably 30,000 because I have a lot of hair. Oh, God, my nose. Yes, post ideas for the show in Discord. And Look a Pig, I will be talking to you shortly once I'm done. An entire show in F orbitals. ScientistMel drinks 3 bottles of wine at 10 a.m. Doing a show on F orbitals. This is Nell C's dream, right? I'm on bottle 3. No, mimosas. ScientistMel drinks 3 pitchers of mimosas talking about F orbitals on a Saturday morning science show. It's hashtag HeyScientistMel. Hashtag HeyScientistMel is my hashtag on Twitter. My ats and mentions fill rapidly on any given day, but I always reserve that just for that hashtag is the best way to hit me up. You can also DM me, direct message me, but don't be sliding into my DMs and like, hey, what's up? I'll be like, yeah, bye. I ain't there for that. We ain't there for that. That's all right. Spectrometer yourself. All right. Oh man, a spectrometer would be cool. DLS. We could also talk about DLS, dynamic light scattering, and Brownian motion, which is a cool thing and something that Einstein mathematically proved. Is not a commonly known thing about that. He proved the existence of atoms through math and Brownian motion. Twitter is obsolete. We have Discord. Oh my goodness. Please consider subscribe. Hit subscribe. Yes, notifications. And look for my new show with Katie Paulson. I'm getting the intro finished. Peter, also known as Gonna Go For It, is making my intro for me. He makes all my intros. I have a really cool rock band known as Versus, fronted by a guy named Craig who lives in Leeds. He's a good dear friend of mine. He's coming up with a rock and roll version of my intro, and they're pulling it together. So every Thursday, I'm going to stream live with Katie Paulson from Pathos, talking about this week in BS. We'll have homeopathy, death dealers. We'll have latest, fads, and we'll talk about stupid things celebrities do, especially with their bad science stuff and a mixed bag of nonsense. So we'll be talking about all of these different things. And check out her blog on Pathos Without a Crystal Ball. And check us out. And I'm hoping to do Spirited Science again. I've secured a venue to where I'll be able to stream live from that venue and help raise money for various charities. I'm just getting speakers together now. That's all I need. Free the girls. Oh my goodness. How much is a mass spec? Oh my gosh, mass specs are expensive. So maybe we could talk about instrumentation. Perhaps that could be another topic for the science of. So I'm going to go because my nose is filling up with horrible things. And my voice is changing. VLA versus Arecibo for astronomy. Okay, I will add that to the list. Burn the curls. No! Guys, can you imagine what I look like with a shaved head? That would be so weird. Don't shave. Mel don't want to shave her head. Maybe there's a hashtag for that. Don't shave Mel's head. Hashtag don't shave your head. Oh my God. Don't shave Mel's head. It'd be terrible. Anyway, metallic hydrogen. I haven't done one on metallic hydrogen. Gene guns. Yes, those would be pretty cool too. Gene guns are fun. Gene guns are a lot of fun. They use that in the GMO world, and I talk a bit about that in my GMO show if you haven't checked it out. Hello, Matthew Tiger impersonator. Hello, talk. Gene guns. Metrology. What is metrology? Scientific definition of mucus, please. It's snot. It's drippy, gross snot. It's just, essentially, it's like a very thickened, viscous substance that comes out of your mucosal membranes in order to counteract any kind of pathogens that would try to enter into those particular passageways, and also to lubricate your passages that are open to the outside environment, mucosal membranes. One of these days I'm going to show up with a wig and see if anyone notices. I bet everybody would. What wig will ScientistMel wear for this particular stream? That would be funny. That would be funny. Gene modding. Yes. Pew pew. Well, you guys are awesome, and this has been a fantastic show. I'm so excited that I get to spend every Science Saturday with you. And I'm going to kind of end with a Mr. Rogers quote because he's one of my role models. You always make each day special for me. You know how? By just your being you. I'll see you next Saturday. And this has been the Science of Atomic Theory. Thank you guys so much for being here with me. This was absolutely awesome. And I'll see you next Saturday. And look a pig, I'm going to talk to you soon. Go check out awesome people like the Godless Iowans, Sci Strike, Andy's Science Show. Check out Godless Cranium. Been on their show recently. Been on Non Sequitur. Mr. Atheist. These are all wonderful things. Apologia, been on his show before. I hop around a lot, and so also every single week I will be on Hannibal and Monty's shit show. Eat honk honk. I said a bad word, but that's in their title, their show. I'll be on there every single week with a little science tidbit. I will post on my, the little science tidbit will go on my account as public once they use it in their show. So every single week on Monty and Hannibal, you can find a little snippet of science related to whatever topic they're covering that particular week. So shout out to them. Thank you guys so much. I will see you guys later. Yes, 2 hours, Sean Holford will go on live. Yay! Have a fantastic Saturday, and I will see you soon. Give you a hug. Hugs, squishy science hugs. Bye.